An important fact to know about Prolog is that we're still preparing it to make it more useful. And you also see this in some of the code snippets I show, which use Prolog features that aren't widely available, at least not yet. Because one of our goals is to make them widely available. I mean, in more Prolog systems, or even at all. And regarding Prolog systems, we have, of course, several desiderata. So it's not only a matter of making features available, but also, for example, to ensure that Prolog systems conform to the Prolog ISO standard. And it's also a matter of searching for and finding the language constructs we want to make available. And we also need to convince implementers to provide them. And of course, Prolog systems should be convenient to use and support, for example, automated debugging based on logical properties. Robustness is another very important aspect of Prolog systems. And in fact, there were Prolog systems that were very fast and had many attractive declarative features, but would crash often or had memory leaks and were therefore only useful as research tools, but not in actual practice, and so on. So we have several requirements for Prolog systems, and they need to be satisfied so that we can actually use Prolog in practice. And our overarching goal is to ensure that the Prolog system is ready when needed. So at some point in the future, when, for example, a company or a government decides to use Prolog, then we must be able to point to a system and say, this is a good Prolog system. It conforms to the ISO standard, it supports all the latest constructs, it's convenient to use, it's robust, fast, and so on. And of course, there already are a few Prolog systems. However, the current Prolog systems satisfy our requirements to quite varying extents. For instance, GNU Prolog and Sixus Prolog fully conform to the Prolog ISO standard. And that's of course very good, because this means, for example, that we can use these systems to test whether our code is portable to other systems, at least syntactically. And both systems are also very efficient, and that's of course nice too. But these systems don't yet satisfy all of our desiderata. So for instance, at least currently, GNU Prolog doesn't have a garbage collector, and Sixus Prolog doesn't ship with the latest declarative constructs. And that's of course completely understandable, because Prolog is subject to ongoing developments and improvements. For instance, new language constructs are found, implemented and adopted, and it takes a lot of time until all systems incorporate them. For example, the SI family of predicates and if underscore have recently become available in Scryer Prolog and aren't yet available in any other system. Whereas many, but not all Prolog systems already ship with declarative integer arithmetic, such as sealbfd and sealbz. And phrase from file is now also already available in several systems. However, it's not only a matter of having such a feature, it should also be implemented efficiently, for example, as in Triella Prolog, where files are directly mapped into memory, and so on. So there's a lot of progress happening in Prolog systems, and of course progress is not always continuous. It happens in fits and starts, and it also includes setbacks. And also, there's some competition between Prolog systems, so they don't always cooperate and align, but also diverge at times. This has always been the case, also because one can make a lot of money by selling a Prolog system. So there's a clear incentive to provide unique features and to outsmart your competitors. And as is often the case, the loudest and most ruthless competitors often attract significant popularity, which luckily is evened out a bit by the fact that popularity can also be a handicap. Because when a system becomes popular, it will sometimes be bought up by a company and simply vanish. And if it's not bought up, then companies will sometimes bribe the implementer to implement things that are only in the interest of that company. And for implementers, it can be hard to resist this temptation. And also, when a popular system goes into a wrong direction, then it will also have many fans cheering it on. And so it can also go astray more easily and so fade away again. So in a sense, popularity is a double-edged sword. And in general, the fact that a system is popular doesn't mean that it's good or noble. It only means that it's popular. And in fact, for many things, popularity is a sign that they are pretty bad. So popularity isn't in itself worth striving for, but surely it's nice when a good system becomes popular. And this is what we should be aiming for and also demand. We should demand more from systems than they currently offer. Not for the sake of popularity, but for the sake of improvement. And popularity will automatically be a consequence of these efforts. For example, let's consider Hello World, because just recently someone mentioned to me that even after reading a lot of material about Prolog, it's still unclear how to do this with Prolog. So how can this be? Because the task here seems simple enough at first. We are to write a Prolog program that emits Hello World on the terminal. And we can of course do this with Prolog using so-called side effects. We ask, for each character in a list, we print the character. And the list of characters is Hello World, followed by a new line. And when we post this, Prolog writes Hello World on the terminal, and this solves the task. However, such a solution has a quite severe drawback, because we can't easily reason about terminal output, because text that only appears on the terminal isn't available for reasoning within the logic program, and therefore you will in all likelihood not write test cases for text that only appears on the terminal, because writing test cases for terminal output is less convenient than writing Prolog queries that reason about rules and facts within the program. And at the moment, this situation is still considered normal, so many programmers are quite used to this situation. Text appears on the terminal and there's no easy way to test the output, and that's simply accepted. So now it's time for improvement, because one of our goals is of course automated reasoning based on logical properties of our code. And this works best if we restrict our code to the pure monotonic core of Prolog. And to do this, we may also need new language constructs. For example, in the future, we'd like to solve this task in a purer way by increasing the declarative parts of our code. For instance, let's describe the output using a DCG. So the text that shall appear on the terminal is Hello Future, and we can state this with a DCG non-terminal. And the advantage is clear, because the text is now amenable to reasoning and testing. For instance, we can ask, what is the text tease that's being described by the non-terminal? And we can also ask more about it. For example, is tease a list whose first element is the atom H? And Prolog tells us, yes, that's the case. The text starts with a capital H. So in this way, we can now reason about the text. And to actually emit the text efficiently, we would benefit from a new predicate, say a phrase to stream, which allows us to write the described text directly to the terminal or current user output without manifesting the entire list in memory. So ideally, this predicate would simply write each character to the terminal as soon as each character becomes known without even constructing the entire list in memory, and then succeed. And in this way, we can decouple pure code from side effects, because we now have a declarative description of the text, and if needed, we can also easily and efficiently write it to the terminal or to a file. So this is an example of a useful future development, and currently there's no Prolog system that provides phrase to stream, and therefore we can't yet satisfactorily write Hello World in Prolog. And this is why I've so far not mentioned this task at all, because solving it requires a construct that's not yet available. So how can it be that essential features and improvements aren't yet available in all systems, or not even available at all? Well, one of the reasons is that the incentives are often aligned to favor local optima. So as an implementer, you'll have to ask yourself, what are noble goals which are worth pursuing? And you'll have to ignore or even actively fight incentives that lead you astray. For instance, it may be tempting to bind customers to your system by creating your own dialect of Prolog. This creates vendor lock-in, favoring one system over others, because application programmers can then no longer port their programs to other systems, at least not as easily. So a more noble approach in this case is to keep to the Prolog ISO standard and only implement so-called conforming extensions. A conforming extension doesn't change the meaning of existing Prolog code, so it can be safely added to each standard conforming Prolog system. And I consider this more noble because it gives all Prolog systems a chance to adopt such extensions. And over time, conforming extensions can also become part of the ISO standard. Or as another example, when you publish about Prolog, then traditionally performance matters a lot, or even most. So even if your Prolog system implements new and groundbreaking features, if it's not fast, then you'll have a very hard time to get papers about it accepted. So When you're working on truly new features, then the incentives may be stacked against you, at least initially. And of course, it's clear that other features besides performance are at least equally important. So at least there's hope that you get a reviewer assigned who understands this. And it's not just reviewers who impose dubious incentives. Often also students like counterproductive features the most. And here, good implementers can help a lot because implementers can promote better approaches with their systems. And in all such cases, you can compromise on implementation details, but you shouldn't compromise the principles. For instance, it should always be clear that we're keeping to the Prolog ISO standard and implement only conforming extensions. And similarly, it should be clear that we don't sacrifice correctness for performance and so on. So what should we do? Well, of course, we have to prepare the right things, right? And that's in fact often easier said than done, because it's quite easy for implementers to lose track, also due to the mentioned incentives. So we have to be careful to move in the right direction. For instance, suppose we want to have strings in Prolog. This is certainly a good thing to have in a language. And what exactly do we mean with strings? Well, here opinions differ already. And the incentives can lead us in a wrong direction. For example, in Marseille Prolog, the very first Prolog system, the string ABC was the same as a list with 3 atoms, each of length 1, where each atom was one of the characters of the string. And as a historical note, the list syntax was different back then, but the important part here is that a string was a list of characters. And that's clearly a very nice representation of strings, because it's very intuitive. And also it means that all predicates over lists automatically also work for strings. And in fact, Prolog was designed for convenient string processing, especially using DCGs. And in fact, that's why the entire formalism was invented. And so it's very understandable that this representation of strings was used in Marseille Prolog. However, not all Prolog systems did this. For example, Edinburgh Prolog used a slightly different representation, where the string ABC was the same as a list of character codes in the local encoding. And this representation is, of course, still useful. It's still quite intuitive, and we can also still use all our list predicates, like append, reverse, and so on. However, answers on the top level are now much less readable, and even less readable in non-European languages, where we often don't know the code points of characters by heart. So this representation is already a step back from Marseille Prolog, but it's still conforming to the ISO standard, because Prolog systems can choose either of these representations, and we can even configure the representation at runtime using a Prolog flag called double quotes. So both of these string representations are conforming to the standard. Now, for comparison, let's consider a string representation that is not conforming to the standard. So when a system adopts this representation, then we can't really call it Prolog anymore. It's something different. So we'll call it pseudo-Prolog, from Greek pseudein, to lie, to deceive. It lies to us and says it's Prolog when it really isn't. And pseudo-Prolog does something entirely different. It treats the string ABC as just a string ABC, which is a new atomic type. So it's not an atom, but something else. And in fact, treating strings as atoms would be conforming to the standard if the Prolog flag double quotes is set to the value atom. But this is certainly not conforming, because this is a new made-up type, which is atomic but not an atom. And this means that we cannot use well-known existing predicates for reasoning about such strings. In particular, since these strings are not lists, we cannot use append, reverse, and so on for reasoning about them. So pseudo-Prolog will also have to provide an entire new set of predicates to reason about strings and call them, for example, string concat, string length, string to list, and so on. And the incentives are sufficiently twisted so that such a system, even though it's Prolog only in name, not in spirit, may even gain popularity, at least in the short term. That's because to many researchers it seems great at first, because they can now publish about the new feature and discuss its implementation techniques and so on. And to many students, it also seems great at first, because they already know such strings from other languages. And also, it's easy to fool many students and make them think that such a strange development is a form of innovation. And so they easily accept it and believe that it's a good thing. And to many instructors, it also seems great at first, because Prolog instructors can now occupy themselves with teaching these additional predicates, which aren't needed at all in actual Prolog systems. And this makes many instructors happy, because it means that there's finally something to teach that everyone easily understands. So also many instructors are happy with this, even if this knowledge is completely pointless and counterproductive, because one of the consequences of this feature is that it makes Prolog harder to teach and harder to learn, because now the situation is more complex, since there are now more predicates and more types of terms. So the situation is rather tragic, because on the one hand, the fast acceptance of counterproductive features shows that programmers feel that the current state is not optimal. So Prolog programmers do sense that there's room for improvement. And on the other hand, it also shows that the desire for quick improvement can lead people away from actual progress. And as good as it may seem at first, this representation is a dead end. It's a technological dead end, because it undermines improvements which implementers should work on instead, and it's a spiritual dead end, because it leads us into a completely wrong direction, away from the use case that Prolog is actually meant for, namely efficient and convenient reasoning about text, especially using DCGs. And DCGs can only be applied to lists. And that's why, very wisely and bravely, the newest Prolog systems, such as Scryer, Tau and Trailer Prolog, go back to the roots and treat strings as lists of characters again. And this is the direction where new Prolog systems should be heading, because in this way we benefit from the full power of Prolog for text processing. So these new systems are now paving the way, and it's to be hoped that other systems will follow. And in every conforming Prolog system, you can already try this out by setting the Prolog flag double quotes to chars. So this is an example where, at least at first sight, the situation may appear chaotic, because it seems that every Prolog system does it differently. And in a sense, that's true. But in another sense, it's not true, because what's happening here is a development over time. And the overall trajectory of this development is pretty clear, even if it's slow, and even if it means returning to the start. So on the horizon, there's the hope of convergence. Now, how do we know whether we're preparing the right things? Because maybe we're accidentally preparing wrong things. And to give some indication about it, let's instead ask, are we preparing things right? Because the way in which we try to reach our goals matters a lot, to such an extent that we could say the way is itself the goal, in the sense that if we go about it in the right way, then we automatically also end up with the right things. And to prepare things right, we follow a few simple principles. First, we always ensure desirable declarative properties. For example, consider the predicate between. Between of 0, 2 and 1 is true, because 1 is between 0 and 2. So we can use between to test whether an integer is between two integers. And we can also generalize this and ask which integers n are between 0 and 2. And we get concrete solutions as answers from the Prolog system. So we can also use between to generate integers. And I emphasize that this predicate is meant only for integers. And consequently, if we specify an argument that is not an integer and ask, for example, which integers n are between 0 and s, then we get a type error. And this may appear somewhat shocking at first, because an error suggests that something has gone wrong here. But in fact, there is nothing wrong here. And this works exactly as expected, because the type error gives useful information when reasoning about the code. It means, for example, that no specialization of the query can make it succeed. So a type error tells us that, if anything, only a generalization of the query can succeed. Now, suppose we are extra smart and overload the predicate so that it also works for an argument that is not an integer, because sometimes we want to simply enumerate integers without any bound from above. And to express this, we could, for example, decide to use sup, the supremum of the integers, as the second argument. And at first, it may seem a good idea if the predicate then enumerates integers, 0, 1, 2, and so on. But if we do this, then it contradicts the type error we just saw, because the type error told us that the second argument must be an integer. And if the predicate also succeeds if the second argument is not an integer, then it means that the type error lied to us, and we can't use it to reliably reason about the code. And in addition, we now have a second problem, because the predicate no longer terminates universally in all cases. So reasoning about code that uses this predicate is now complicated to such an extent that it's no longer feasible, because we can't rely on what the type error tells us, and also the predicate now causes non-termination. So it's much more desirable to throw a type error in this case too, to preserve logical properties that allow reasoning about the predicate. Another important principle, and let's call it principle A, because it's at least as important as principle 1, is to combine convenience with efficiency. For example, suppose that, as in the case above, we actually want to enumerate natural numbers and accept that it doesn't terminate. Then the way to do this is not to destroy the nice termination properties of between, but rather, for example, to use the predicate length. We don't care about the list, but only about the length n. And in response to this most general query, we get every n for which there is a list of length n. So we get 0, 1, 2, and so on. So we can use length to generate natural numbers. And ideally, implementers make this case efficient, space efficient, so that internally the lists aren't even constructed in memory, but only the lengths are generated as integers. So this is an example where implementers can help us to combine convenience with efficiency, because it means that we can simply state what we mean, and internally the system makes sure that it runs efficiently. And strings are also an example of this principle, because if you think about it, then it's rather clear that lists of characters are the most convenient representation of strings, and implementers should also make it efficient. So regarding the earlier question about the right thing to do, the answer follows naturally already from this principle, because we want to combine convenience with efficiency. And the earlier pure I/O example is also an application of this principle, because testing should be convenient, and therefore we want to increase the pure parts of our code. And so implementers should make pure code also efficient. Constraints are another example of this principle. Here, implementers should make the implementation of constraint solvers convenient and efficient. For example, by providing interfaces for attributed variables so that writing constraint solvers is convenient, and at the same time, constraint solvers are acceptably fast, and so on. And finally, maybe the deepest principle and probably hardest to understand for implementers: keep to the main road. By this, I mean, to promote Prolog, we must use Prolog. Okay, maybe use sounds a bit exploitative. So at the risk of sounding tautological, let's rephrase this to promote Prolog, we must promote Prolog. And I emphasize this because for implementers, it's easy to get sidetracked, and I strongly recommend to avoid this trap. Especially that if you implement a Prolog system, then an ideal design goal is to implement as much as possible in Prolog itself. For example, the architecture of GNU Prolog is a masterful application of this principle, because large parts of GNU Prolog are written in Prolog. And keeping to the main road is easy, but implementers tend to get sidetracked. And indeed, there were great Prolog programmers who wanted to make the system more efficient and began to implement more and more of it in lower level languages, only to make it faster. And after 20 years of this, they were among the world's top C++ experts, but they had completely lost track of their initial goal, which was to improve Prolog implementations. So to promote Prolog, use Prolog as far as possible, and don't fall for other formalisms. And if Prolog isn't fast enough, then work on that and improve the core to make it faster. Because only in this way do we get fast Prolog systems that can be applied more generally. Now, why is this all taking so long? Why do we still have no freely available Prolog system that satisfies all our desiderata? Well, first of all, it's hard. Implementing a Prolog system takes a lot of work, because you have to implement all kinds of features reliably. And there are also a lot of trade-offs involved, for example, between speed and robustness of the system. And also, our demands on the Prolog system change over time, since we understand Prolog better as we use it more. For instance, consider again Marseille Prolog, the very first Prolog system. In Marseille Prolog, a type test on a variable would yield an instantiation error to preserve desirable declarative properties. Now, suppose you are a customer in the 70s or 80s and you're one of the first people who see such a new and quite strange error. No other programming language has anything like it. So you're shocked and think that there's something wrong with the system. And in Edinburgh, a different Prolog system is developed called Edinburgh Prolog. And in Edinburgh Prolog and its derivatives, including the ISO standard, when we ask, is the variable x an integer, we get false. Now, the customers who are still shocked by the instantiation error are now very happy because there's no longer any strange error, just silent failure. And life goes on and customers continue to be happy. Everyone gets used to the new approach. Type tests yield false for logic variables. And after some time, customers want more. For example, more and more frequently, customers want to reason logically about their code, because they're starting to realize that it's easy to reason logically about Prolog code, and especially to write Prolog programs that analyze Prolog code. Now, suppose we have a few goals, then the goal x is equal to 3, then a type test, which is true if and only if x is an integer, and then more goals. And now we want to systematically reason about our code, for example, because we're trying to locate a mistake in our program. And what matters for the analysis is that we can rely on strong logical properties, otherwise we can't analyze the code systematically. For instance, in this case, suppose we generalize away a goal. Then certainly from a logical perspective, we expect the fragment to become more general, in the sense that the set of described solutions increases or stays the same. But here, this isn't the case in general, because the predicate integer is not monotonic. This means that even though we have generalized the fragment by removing a constraint, the generalization may fail even when the original fragment succeeds. And that's of course extremely unfortunate, because it prevents us from applying logical reasoning to the code itself. And at this point, customers change their minds and say that we are no longer happy because what previously seemed like a good idea, in fact, was not. And this is the reason why in newer Prolog systems, like in Scryer Prolog, we now have the SI family of predicates, like integer SI, atom SI, and so on. And these predicates are like the type tests in Marseille Prolog. They yield an instantiation error if the argument is a variable. And this means that they preserve the desirable logical property of monotonicity. We can generalize a predicate by removing a goal. And that may cause an instantiation error, but it certainly cannot cause silent failure if the predicate previously succeeded. So we now have a reliable declarative property, and that comes in handy when analyzing programs and locating mistakes, and this makes customers happy again. And another reason why this is taking so long is that acceptable trade-offs also change over time. For instance, unification speed is very important when you are CPU bound. However, nowadays, unification speed barely matters at all because so many tasks are now I/O bound. So what matters is rather how efficiently can we reason about data that resides on disks, and how conveniently can we reason about data that arrives over a network and so on. And this is one of the reasons why nowadays making unification slightly slower is totally acceptable if it makes reasoning about strings and file contents more convenient and more efficient, especially space efficient. So this is an example of an improvement that's much more acceptable today than it would have been 30 or 40 years ago. So overall, working on Prolog now means to practice the art of preparation, because it takes at least decades to implement a useful Prolog system, and we now use the time to prepare a few of them. And just to emphasize this once more, this isn't something that will be finished in the near future. It will take a long time. And indeed, it would be nice to have a few great Prolog systems in 20 or 30 years from now. And personally, I have no interest in what's popular today. For me, what counts is to prepare a system for the future. Because even if 20 or 30 years may seem like a long time, the future will stretch on far beyond. And so the future is well worth investing into. And one of our goals is to have a good Prolog system available when interest in symbolic AI resurges. And that's not a matter of if, but only of when. Because there are many application areas where symbolic AI will be needed in the future. For example, in use cases by governments and lawyers, where the issue is typically not to guess the laws from data, but rather the key issue is to automate the execution of existing and well-known laws. And a few important milestones on this journey are, first, to have Gupo running in a free Prolog system. Gupo is a teaching environment that runs on Sixtus Prolog, and so far there's no free Prolog system that has all the necessary features to run it. So when Gupo becomes available in a free Prolog system, we'll have a very effective system for teaching Prolog. Then list comprehensions are another important milestone. Currently, it's still unclear how to add them to Prolog, but there's of course hope that it's possible. Then building on pure I/O, it would be nice to have logical ORG as a generalization of ORG for string processing. Built-in parallelism would of course also be nice, and so on. So a fitting motto for Prolog development would be prepare it. And we prepare it serenely, and we don't hurry. We make the right building blocks available so that programmers can realize the full potential of Prolog, knowing that it will take a long time.